I think we are all now ready to step into the technical part of this meeting. And we have chosen to have an inaugural lecture to warm up the rest of the technical program, which will be very intense, as we have already mentioned. And for this inauguration lecture, we have chosen, it should be presented by Professor Tinsley Oden. And it is really my pleasure to introduce Tinsley, that you all know, so it needs very short introduction because it is one of our leaders in the field of computational mechanics. He was the founder of the IACM, one of the first presidents, and he has, from his civil engineering background, from his pioneering work in structural mechanics, he has developed a really tremendous career in the field of mathematical modeling, numerical methods, in computational techniques applied to solid mechanics, fluid mechanics, error estimation, biomedicine, and recently stochastic computational techniques. So I'm very pleased and honored to introduce Tinsley. It's our great pleasure to have you in Barcelona. So Tinsley, thank you very much for being with us today.
Thank you. It's really a great honor for me to lead the technical presentations in this very impressive meeting. I can't recall an opening session that was more exciting and more surprising. I was asked to give a talk on current work which has to do with the emergence of predictive computational science. And I'll explain what that means as I progress through this. The work is in collaboration with a number of people. I mentioned Catherine Farrell, who will give a similar, shorter talk on Wednesday that has a lot of details I will not be able to cover. Daniel Fagahi, who's a postdoc at ISIS. I'll cover 7 topics, if time permits, ranging from a few definitions on the logic of predictive science, what is it and why now, and I'll show applications to one of the most complex problems facing computational science, and that is multiscale model, the tyranny of scales, and why that represents an extraordinary challenge in predictivity. I'll make an argument that this setting is best approached in a Bayesian setting. I'll talk about a predictive process, look at some examples. We'll talk about the confounding issue of model inadequacy, which you may be surprised to know affects virtually all the models that we come into contact with in computational mechanics. And then I'll have a few conclusions. So what is the logic of predictive science, and why would anyone dare say science is not predictive? That's what science is all about. To predict the future. Why do we think it may not be predictive, and there's any meaning to look at the foundations or emergence of predictive science? Well, I define predictive science as the discipline concerned with assessing the predictability of mathematical and computational models of physical events. It embraces the process of model selection, calibration, validation, verification, and their use in forecasting the features of physical events with quantified uncertainty. Models here means the mathematical model. It means a set of mathematical constructions motivated by some principles, or maybe even empiricism. that we use as the basis for inductive hypotheses. What do we mean by calibration? Well, the same old definition we always use. You adjust the parameters of a model to reveal laboratory experiments. And validation, I'll give a short definition now, is a much more complex idea, requiring a much more careful definition. But for right now, I'll merely define it as the process of determining the accuracy with which a model can predict features of physical events. And when I say features of physical events, one must come to the realization early in this business that to determine the validity of a model, one must specify the target application, the quantity of interest. What is the goal of the model? For one model may be perfectly valid and accurate for one goal, but completely unsatisfactory for another. And why is the issue of predictivity come to the forefront over the last decade? I submit it is because of computational mechanics itself and its advances. Over the last 2 or 3 decades, we have learned that the equations, models of classical physics, classical mechanics, can be extended beyond the realm we ever dreamed of only a little while ago. And so we've been inclined to trust these models, extend them to make predictions and designs of systems that were not reachable in the short past, only to find out that many of our most treasured models are not very good, may not be very good. And some of these decisions are life and death decisions that we must make with the predictability of models. One of the most obvious is the nuclear test ban. We don't test nuclear systems anymore. We model them. And so the prediction of these models is an area in which billions of dollars and billions of euros have been spent. How good are our predictions? What about the accidents that we observed over the last decades due to flaws in predictive methods? Anyone here think we can predict the weather or the climate? What about predictive surgery? Would you dare put in the hands of a surgeon a predictive model, certain that the predictions of that model are accurate enough to do processes that affect life and death? Well, a simple answer to predictivity is knowledge. The more you know about a system, the more likely you can trust your predictions. And the knowledge of physical laws hits at the very essence of science. Science comes from the Latin sensio, to know. It's the systematic activity, or the activity concerned with the systematic acquisition of knowledge. Over the last 2 millennia, we have learned that knowledge can be obtained basically in 2 ways. We've added a third recently: theory, or inductive hypotheses; observation, that's empiricism, experiments; and now we've added to the tool chest notions of computational science, where we make models and simulation, and we can go beyond what can be physically observed, and we can go beyond and exercise many different models of physical behavior. So the scientific method, more or less out of Oxford Dictionary, is the method in which statements are tested that are logical consequences of scientific hypotheses, theories, or related computer models and simulation through repeatable experiments and observations. So we're led back to the notion of logic. What is logic? Logic is the study of reasoning. It goes back 2,400 years to the writings of Aristotle. It's the process of reasoning from one or more general statements, axioms, or premises to reach certain conclusions. And I emphasize the word certain. We now accept deductive logic as the foundations of modern mathematics. The idea is that it's top-down logic in which you state an axiom and through the rules of logic uncover what the consequences or what the implications of those axioms are. Science is really based more on inductive logic, bottom-up logic. The process of reasoning generalized by extrapolation from initial information and hypotheses. Inductive hypotheses can be wrong. If they're found to be wrong, they're revised. And the revisions are used until contradictions are encountered. So once a hypothesis is laid down, deductive reasoning takes over because you explore the consequences of those hypotheses. What has confounded modern predictive science is not that we can't lay down reasonable hypotheses, or not that we have not learned methods of deductive logic that can explore the consequences, but rather at every turn we encounter uncertainties. So to go from knowledge to prediction, we must do what? Well, I just said that observations, the word observe, or observations, means to detect with the human senses, aided generally by instruments. And both of those are subject to errors, observational errors. And we use inductive reasoning, theory, mathematical models, to characterize properties of physical realities. And of course, all models are wrong. Finally, we corrupt those models a step further to make computational models. And on the basis of these very corrupt models, which face uncertainties at every step, we make a prediction. So with this perspective, prediction is indeed a very difficult subject. It requires care in handling the uncertainties in all aspects of the scientific method. How do you handle uncertainties? There's not a unique answer to this question. The most logical question, and most of us would agree with, is that we use probability theory. We develop a theory based on the foundations of probability theory. But what probability theory? We subscribe to the probability theory laid down in a famous theorem by R.T. Cox in 1946, in which basically, in essence, Cox's theorem says that every natural extension of Aristotelian logic with uncertainties is Bayesian. This is a profound result. It's been a subject of debate ever since it was published. It's the result of an ingenious proof that even today is debated. Basically, the idea is that we introduce the notion of a plausibility of a proposition. And in Cox's original paper, he laid down 4 desiderata. Desiderata are desired properties, very innocent-looking, common-sense properties. And the one ingredient that he added to the notion of plausibility is conditional plausibility. We make assumptions based on prior information. So we have a proposition A and a proposition B. And we have prior information X, where X is consistent with these propositions. Consistent simply means it cannot apply that the proposition is both false and true simultaneously. And on the basis of these conditions, in this long and ingenious proof, we arrive at the conditions of plausibility. Namely, the plausibility of a proposition A given X is 1 is 0 if it's false, 1 if it's true, and if you can scale it, it's some number between 0 and 1. It's a real number, by the way. But most importantly, the conjunction of two hypotheses, the conjunction of two propositions, has a plausibility condition on X equal to the plausibility of A given X times the plausibility of B given that both A and X are true. That's a conclusion. It's called the product rule of Cox's theorem. That's Bayes' rule. So Bayes' rule came as a natural consequence of a sequence of logical steps derived in the 1946 paper by Cox. Well, this topic has been debated ab initio for the last 40, 50 years. Halper wrote a paper saying, giving a counterexample. And then he gave a counterexample to the counterexample, and that was refuted by another paper by Van Horn. Many papers have been published in between on exactly how to interpret Cox's theorem. A very excellent paper is Kevin Van Horn's paper called Constructing the Logic of Probability. Edwin T. Jaynes' book on probability theory, The Logic of Science, is based on this. And many other papers I mentioned, Dupree, Tipler, a wonderful book by Sharon B. McCraney on the theory that would not die, by Bayes' theorem, a powerful sequence of papers by Klein and Vandervoort on asymptotic approaches using Bayes' theorem, and then more recent papers by Arwadi and others on Bayesian brittleness, and why no Bayesian method is good enough. Also countered by arguments in the papers by Klein and Vandervoort. So that's Bayes' theorem. It's on page 1 of every book, or page 2 of every book on probability theory. It's a very elementary idea. The probability of A given B is the probability of B given A times the ratio of P of A over P of B. Thomas Bayes was a Presbyterian minister. He died in 1761. He wrote this paper, an essay towards solving the problem of the doctrine of chances, and it laid on his desk for 20 years. He never published it. One now looks back on his work and hypothesizes that the reason Bayes did not publish this work is he thought it had buried in it the existence or non-existence of God. Cause and effect. Given prior known conditions, given hypotheses, what can it project into the future? It's an ideal framework for predictivity. The executor of his estate, Richard Price, eventually published the work 2 years after Bayes' death. About a dozen years after this, the work of Laplace on probability theory began to emerge. Slightly different than Bayes, but eventually coincident with Bayes, when Price went to Laplace and explained that, oh, you've been leaving out the priors. You're getting the frequencist approach to statistics. If you include the priors, it's a much more powerful framework, which includes classical statistics and probability as a special case. So one starts with a model. P is a model. Theta is a collection of parameters. A model, I said, is a collection of equations or inequalities or mathematical constructions. It depends on parameters, so we call it a parametric model. The model is applied over a scenario. A scenario means the domain of the solution, the initial or boundary conditions, and you must assure that the model has a solution. If it has a solution U, it will depend on the parameters and the scenario on which the model is applied. Now, if you take Bayes' theorem and you look at probability measures that are absolutely continuous with respect to the big measure. You can come up with probability density functions in terms of the parameters of a model. So this is a probability density. That's the parameter. This is the data that you observe. And so the posterior is the product of the likelihood and the prior over the evidence. This is just rewriting Bayes' theorem in terms of densities, parameters, and data. So if you go to the physical universe and you measure a physical entity at a point, let's say the temperature, the data that you require for this observation is of course wrong, because there is experimental error, I've assumed here to be additive, in the measurement device. And then you have a model. Of course, the model is wrong too. The model is a function of the scenario and the parameters, and it fails to measure reality by an amount called the model inadequacy. So the total error is given as some probability density P times the difference between the parameter to observation map and the observations. And that's called the likelihood. Why is it called a likelihood? Well, this is a probability. If you provide the value of theta, the parameter, this gives the probability that the observation is true, the likelihood that the observation is true. I'm going to be talking about a really complex set of applications. These are multiscale models where we start from sort of ab initio, all-atom model of an atomic system. We lump them together into a molecular model, and we eventually average or homogenize the molecular model to get continuum models. And this process involves every possible complexity that you can have in predictive science. The confluence of all challenges in predictive science. What is a model? Is it valid? What does valid mean? And what is the level of uncertainty in the prediction? I will jump from time to time to this application. This is a nano-manufacturing application. It sort of emphasizes the point. If you look at these little nano features in this manufacturing process, these little guys are only 30 to 70 nanometers in dimension. So if you pick one piece of those and take a 30 nanometer cube, they're around 600 atoms. It means you have 216 million degrees of freedom. It's not really enough to gather mechanical properties yet. If you integrate that over 50 or 5,000 or 10,000 time steps, you're quickly manipulating trillions and trillions of data, data points. And no one does that, except in rare, very special cases. So what do? You lump everything together. You go from the atomistic model to a molecular model, where you lump the atoms together and you reduce the number of degrees of freedom from 648 million to maybe a few thousand. And those are manageable in modern computers. So the idea is you get a bunch of atoms, you lump them together and aggregate them from a map G, and now you work with the molecular model. But how do you do the molecular model? Well, most chemists now will tell you, I know how to make a molecular model because I've been working in this area for 50 years and my judgment tells me how to do it. Is there a systematic way to lump atoms into molecules? Because given a complex molecule, we have many, many, many different possibilities for reducing the atomistic system to a molecular system. And I can point to cases in the literature, many, many cases, where different investigators will choose different aggregate models for the same application. But that's only half the story. The rest of the story is, what are the potentials? What are the interaction potentials between these molecules? This is one I took out of, this is a rather standard one, out of one of the many hardened molecular dynamics curves. This is the internal energy. It's a function of the parameters. You have your harmonic bonds, your angle bonds, your dihedral torsional bonds, your non-local bonds Litter-Jones, and Coulomb bonds. In any one of these models, you will find a list of unknown parameters. Most of these parameters are guessed at, or determined at a handbook. Of course, once you have a molecular model, you must average its property to determine a macroscale model. So if these parameters are wrong, I can assure you these parameters are also wrong. And now the remainder of the problem is this. Since you don't know the form of the internal energy, you can say, well, one possibility, I have this, I have an angle bond here, I have a covalent bond there, I have a non-local bond there, or I have some other combination of these, leading to a large number of possible models to draw from before you even start the problem of prediction. So here you have a model class. P stands for the model. Theta stands for the parameters of that model. And each one of those P's stands for a different possible configuration of the interaction potential. So for simplicity, we have a model class. Let's say M models with M sets of parameters. What is the model? Well, basically the model is either Monte Carlo methods or molecular dynamics methods. There are 4 or 5 molecular dynamics codes that are used internationally. There's AMBER, there's CHARM, there's GROMACS, there's LAMPS, and others. They all have a table of these potentials, and one chooses the parameters from the potential, and you solve Newton's equations for the motion of n particles. If you happen to know the probability distribution over the phase space for the all-atom model, you can compute ensemble averages of phase functions. Or if you use molecular dynamics, you can use time averages over a calculation of the distribution of momenta and coordinates of molecules in the model. So for the coarse-grained model, you have some approximation of the quantity of interest. It involves some distribution, probability distribution. For example, this could be this Boltzmann distribution. It involves a phase function, which is your quantity of interest, and you may evaluate that either using statistical mechanics or molecular dynamics using an ergodic hypothesis. Now, one quick thing I will insert here is that molecular dynamics involves a system of dynamical equations for the coordinates of the atoms. The lumped involves a system of dynamical equations for the coordinates of the molecules. If you differentiate this equation, you get the Hessian of the internal energy and the equation for the adjoint. And if you compute the residual, there's a cheap theorem you can get here, that the error between the observable ensemble average and the approximation to the coarse model is always given by the work done by the residual work done by the coarse-grained model on the solution to the adjoint problem. The implications of this theorem have not really been fully explored. It's possible it has something to do with the minimum entropy principle I will discuss subsequently. Now we get to the application of Bayes. My Bible is the book by Edwin T. Jaynes, also published 2 years after his death. Actually, it was 5 years after his death. He has this, among many quotes, the essence of honesty or objectivity demands that we take into account all of the evidence we have and not just some arbitrarily chosen subset. You can't imagine how important that observation is. It tells you, it leads you toward using all information you have on the parameters and the characteristics of the model. Because the Bayesian framework gives you an opportunity to test whether the use of any of the information you have increases your information for that model. I like to think of the prediction pyramid, where you start at the bottom of the pyramid with observations for calibration. S sub C is a calibration scenario, and you move gradually up the pyramid until you arrive at a scenario for the validation of the model. This validation of the model must reflect the quantity of interest. That's the key. So you start off with prior information on parameters, you update those with calibration, and then you construct informed validation experiments to finally determine the extent to which those parameters apply to the quantity of interest. At the peak of the pyramid is your extrapolation into the future, the quantity of interest, the prediction. And in general, you never know that. You never know the prediction. If you ever measure the prediction, you're cheating because it's no longer a prediction. It becomes part of the observational data. The reason that Bayesian methods have suddenly in the last 20 years become so popular is the advent of the computer. And Markov chain Monte Carlo methods. So all of these complicated formulas with densities are sampled using one or more sampling methods. So if you're going to implement a statistical analysis of parameters and model uncertainty, you need to have at your disposal a sampling algorithm, and we have a very good one called Queso. So you start with a prior, you go back to Bayes' formula, and you have observations for the calibration. You have a prior. You compute the posterior, that becomes the prior for the validation, and you update the parameters again. And once you're content that you're sufficiently close to the observation, then you jump out into outer space and predict the quantity of interest. It in itself is also a probability density function. So you start with an inverse method. This is a statistical inverse method. You say, what is the likelihood? What are the priors? How does one compute the posterior? Is the validation experiment well chosen? Has it resulted in information gain over the calibration? What is the criteria for validity of the model? How do we solve the forward problem? And how do we quantify uncertainty? I'm going to go over every one of these step by step. First, the prior. The biggest criticism of Bayesian methods 10 years ago, maybe 20 years ago, was how you get the priors. If you know nothing about a problem, the convention is you use a uniform prior. That's the worst. But there are systematic methods to construct priors. They're based mainly on the idea of entropy, information entropy. Entropy is distinct. It's not part of Bayesian statistics. It's a new tool. It was laid down by Claude Shannon in 1948. And he also adopted an approach very similar to Cox. He put in 4 desiderata. I want to find, he said, a logical measure of the amount of uncertainty in a probability distribution. I wanted to have 4 basic properties. Real number, continuous, it obeys the rule of common sense. What does that mean? It means it does not conflict with deductive logic. It's mathematically correct. And finally, it's consistent. 2 different approaches leading to the same number. 2 different approaches must lead to the same number. And so the only function satisfies these desiderata is the information entropy. If you have a discrete probability distribution, it's minus the sum of pi log p, or minus the integral of p log p over some scaling function. Moreover, the entropy is a maximum. The probability distribution that satisfies this maximizes this function. So this is the maximum entropy principle. If you have 2 probability distributions, P and Q, their relative entropy is the famous Kovac-Lightweight distance or divergence, integral of P log P over Q. Claude Shannon had a colleague by the name of John von Neumann, and he was debating, what do I call this thing? And the legend is, by Norman says, it looks like entropy to me, let's call it entropy. And indeed, it's almost identical to the entropy one encounters in statistical mechanics. So, what you do is you find constraints. If you knew the mean of a parameter, that's a constraint on the entropy. You use Lagrange multipliers and you can construct a prior. If you know the variance, you can construct another prior. And this whole process has now become very sophisticated. You can get prior information from the all-atom model or from experiments on equilibrium distances, spring constants, equilibrium angles, and other things, and develop histograms which determine prior probability distributions for a Bayesian statistical calibration. Part 2, how do you determine the likelihood? R.E. Fisher in 1922 said the likelihood that any parameter should have any assigned value is proportional to the probability that if this were true, the totality of all observations should be then observed. It's a mouthful. It's what I said earlier. If you give me a parameter, what is the likelihood that that parameter produces the observation? If you have independent, identically distributed samples, the likelihood can be represented as the product of probability distributions for each component of the sample. And it's very common to take the logarithm of that and reduce it to a sum, because the logarithm and the product have the same maximum. And the essence of frequentist statistics is to compute the maximum likelihood. So you compute the theta that gives the maximum value of LN. Now, what is normally thrown under the rug is the denominator in Bayes' theorem. That's called the evidence. It's nothing but a normalizing constant. Oh, no, no. In fact, the evidence is the most important component of the whole formula. If you go back to the evidence, suppose now I have M models. I go to model P sub j, it has parameters theta j. I'm going to rewrite Bayes' theorem, saying that I have additional knowledge. I have prior knowledge of the model I chose and the class of models to which it belongs. If you write out Bayes' theorem again, it's absolutely adding nothing but notation and recognizing the fact that I have additional information. Then you see that the denominator is the marginalization of the numerator, which is the product of the likelihood and the prior. And then you observe in the conclusion that you have another form of Bayes' theorem on the discrete scale. If I have M models, one of those M models may have a higher evidence than the other. So one computes the posterior for this discrete class. There's the evidence. Notice it depends on the model you chose, the observation, and the class of models that you are examining. And we call that the plausibility, the model plausibility. The remarkable thing is that because it's a probability function, a discrete probability, its sum must be 1. So of all those models, the ones whose plausibility is closest to 1 are the most plausible. I'm enamored by this. I think it's a remarkable result. It's been around for 20 years, but not widely used. James Beck used it. You can find traces of it in the writings of Jaynes. But I don't think it's been used as a tool very much until very recently. It's a remarkable method that allows you to select models among a large class of models if you have the means to calculate the plausibility. So let's go back to our discrete problem, our nano-manufacturing problem. We pick a little cube out. Let's suppose our goal is to find the total energy per unit volume. We do one realization of the molecular system. We look at it, we find that throughout this system, there's a set of polymer chains and crosslinks. I call those representative polymer chains. What you find is it depends strongly on the temperature. You change the temperature, everything changes. So for a fixed temperature, this would be so-called canonical ensemble, you can find these polymer chains. You pick out these polymer chains and you split them into pieces. By the way, here's one of the chains. That's the molecular structure. That's the atomic structure. That's the molecular structure. And you pick out of the polymer chains building blocks. These are 3 building blocks that build almost all of those chains. These are the building blocks I will calibrate for a particular choice of these particular molecules. So, one example of a chain built up these building blocks, 827 atoms, 503 parameters. For the coarse-grained system, you have only 61 particles. You still have a lot of parameters. As a matter of fact, if you look at all possible models, covalent bonds, angles, dihedral angles, non-bonded Lennard-Jones, you have 15 possible models in those 3 units. And they have up to 158 parameters, which is virtually impossible, 158 parameters. There are problems now under certain severe assumptions of solvability parameters. And a problem like this, 158 parameters, is an extraordinarily complex problem. So we try to eliminate some of the parameters using sensitivity analysis. There's several books on sensitivity analysis that have come out in the last 2 or 3 years. There's sort of quick and dirty methods to determine which parameters are least sensitive, determine which parameters least affect the quantities of interest. I've listed a few here. There's 2 books by Aristotelian and company. Most recently, there's a method based on entropy-based sensitivity. One out of Aristotelian's book is the so-called output variance. So you have some output function. In our case, it's the total internal energy for the coarse-grained model. It depends on the parameters. You do a Monte Carlo characterization of parameters. You just put in 50,000 samples of the parameters, and you calculate the sensitivities. By the way, let me point out, you get these scatter plots. So this is the parameter, this is the output, and if you see a scatter plot like this, you breathe a sigh of relief, because it means that there's no pattern at all. This parameter barely influences the output. Where, on the other hand, a pattern like this suggests maybe it does influence it. So if you take, in our case, I took a model of polyethylene. It has 10 parameters. The dihedrals, these are these angular torsion modes between molecules, practically do not affect the total output at all. But I don't completely trust that, so I do a calculation, I compute a trial case, and sure enough, I find that the total change in potential energy, including dihedrals, is the blue line, excluding them is the red line, and as far as I'm concerned, the DKL distance between those two is 0. I'm going to eliminate the dihedrals and therefore go from a 10-parameter model to an 8-parameter model. And so the use of a sensitivity analysis can dramatically reduce the number of models. So going back to my problem, I have a sequence of scenarios. These are calibration scenarios. They differ only in the phase space in which I'm computing the quantity of interest. This is the internal energy for the all-atom model. This is the internal energy for the coarse-grained model. This is the Boltzmann distribution. And of course there's theta. And you calculate the DKL distance, the divergence, between the density of the coarse-grained estimate of the observable and the known estimate from the all-atom model. If that's less than the tolerance, you declare the model valid. Now, I hesitate to use the word declare the model valid, but people do. It's valid with respect to that tolerance and that measure. If you change the quantity of interest or you get new information, it may be invalid. So technically speaking, the best you can do at this point is to say that the model is not invalid. So when I use the word valid, I mean not invalid. Going back to hexane as an example, you have 20 atoms here, hydrogen and carbon. You lump them into 3. You look at the possible number of models, possible number of parameters. You go through the process of computing the plausibilities, which is not a small calculation. Only 2 of the plausibilities were significant. Model 3 and Model 5 had a plausibility of around 0.5. Notice that the most plausible model does not necessarily have the most parameters. Depends on the quantity of interest. And so now you go through the calibration process, and now you check to see, is the distance satisfy your tolerance. In this case, this is the coarse-grained PDF for the quantity of interest. That's the all-atom thing. We chose that a tolerance, 5% of the variance, is satisfied. It made it less than 5%, so we said the model is not invalid. Notice that validity depends upon you choosing a tolerance. You can't just look at a curve and say, it looks good to me. I think in its interest of what Jaynes calls honesty and objectivity, you must specify your tolerance prior to making the calculation, and you must determine if you've passed the tolerances for this calculation. Here's another example. This is plexiglass, PMMA. That's the very complex atomistic structure, 72 parameters. You lump those into 2 charge-free molecules, come up with a table of parameters, and so forth. Now, once this is done, we can lump these together to do the test on a conglomerate of atoms where we're going to take averages and construct parameters for the continuum model. I've got about 2 more slides, Eugenio, and I want to end the talk with a discussion of the misspecification of models. Most of the literature in mathematical statistics assumes that there exists the truth. There is a model for which, if you just had the right parameter, you would hit exactly the right quantity of interest. Of course, that's not true. What is true is that the measure of the truth may lie outside the range of the model. That's called a misspecified model. And there is a misspecified model theorem that says that the posterior will converge to a normal distribution with covariance matrix given by this. This is a version of what's called a Fisher information matrix under certain conditions. So we've been able to prove a few theorems. One, under some conditions, if model P1 is more plausible than model P2, and the initial odds model odds is less than or equal to 1, then the DKL distance from 1 is less than 2, so you're closer to the truth. You'll never get to the truth, but you're closer. And finally, if the distance is good enough and the odds are greater than or equal to 1, then model P1 is more plausible than model P2. And finally, if you have a set of models and only one is specified and all are unspecified, it will always be the best. It will always contain the parameter that minimizes the DKL distance to the observation. There's some other work on asymptotics I will skip. I will go to my conclusions. Very quickly, Bayes' theorem provides a fundamental framework for dealing with model validation and certainty quantification. The test of model validity can involve a sequence of statistical inverse problems for model parameters. Validation is a process of determining the level of confidence one has in the ability of a model to predict quantities of interest and the accuracy with which that model predicts specified observables to within preset tolerances. Plausibility provides a powerful tool for determining potentials, choosing models from a class that have parameter closest in DKL to true distribution. And model inadequacy can be attributed to misspecification. I'll make one last comment now on the slide. working on this a year or so, trying to look at the validity of coarse-grained models. I would say I emerged from that very concerned. I think many of the coarse-grained models that you see in the literature are extremely qualitative. They can at best give only very qualitative information on behavior of molecular systems. Many of those models should be subjected to rigorous validation tests and calibration tests before they're used in any significant engineering application. With that, I'll close, and I'll thank you for your kind attention.
Thank you very much, Tinsley, for this really extraordinary lecture, illuminating lecture, applicable to all the methods and models that are going to be presented in this Congress and beyond. Tinsley has written a little note on this topic found recently in the IECM expressions bulletin that you can collect outside and also through the IECM webpage. And with this, I think we have to close this opening section that I think, from my perspective, has been extremely interesting. Thank you very much.